right, so now we are going to be talking about concentration and some calculations that go along with it. First off, when we talk about concentration, sometimes we talk about it qualitatively and sometimes quantitatively. And qualitatively, we'll do that using two terms, dilute and concentrated. And dilute means that when we talk about a solution, if we say dilute or dilute, means that there is a small amount of solute. Oops. Let me get that in there. Small amount of solute. So if somebody says, oh, that's we've diluted that solution, that means there's a lot of solvent and not a lot of solute. Now, if they say that that's a concentrated solution, like if there's some orange juice concentrate, that means that there's a large amount of solute and not as much solvent. So when you have concentrated orange juice, that means that they've taken the water out and you'd have to reconcentrate it, meaning you'd have to add more water to it to get it to be at the point where you drink it and have it taste like orange juice. All right, so those are qualitative descriptions that we use to compare the concentration. Notice there were no numbers used, and so, those are good descriptors, but in chemistry we like quantitative descriptors. And so to do that, there are a lot of different units for concentration, but in this class for right now, we're only going to be using molarity. Molarity is going to be our go-to unit of concentration. When you see the unit for molarity, it's going to be a capital M. And so you need to be very deliberate in your writing of the capital M. It needs to have points on it to make sure it's a capital M. It is our most common unit for concentration, and it refers to the number of moles of solute particles per liter of solution. And so we can write it as moles per liter, or again, that capital M. So typically you're just going to see it as a capital M. So if you see, if you remember in the lab, sometimes you'd see a number 6 and then a capital M. That means 6 molar is how we say it for short. 6 molar solution. That means its molarity is 6. That means 6 moles of solute per liter of solution. A lot of times we're given grams, so you'd need to use molar mass to convert to moles using dimensional analysis. One thing that I do want to show you, if you remember when we talked about density, we used our triangle just to kind of quicken things up for those of you who are a little, what did we say, a little algebra. What did we say? D equals M over V. We said you struggled a little bit in algebra. We can also take this over to use for molarity, to help us out for molarity. If you could use this for molarity, moles over liters. So one thing I would say is knowing that if you have grams, you're going to need to go to moles, and if you have milliliters, you're going to need to go in and out of liters to milliliters there. So maybe that'll help you. All right. So let's look at our first sample problem. What is the molarity of a solution made by dissolving 50.0 grams of NaCl in enough water to make 1.25 liters of solution? First thing I'm going to do real quick is tell you that I'm going to shortcut and we're going to do the molar mass of NaCl real quick. And I believe it is 58.44 grams per mole. Just to make things fast. All right, so they want the molarity. To get molarity, we need moles over liters. We don't have moles. We have grams and we have liters. So if we go back and we know we need molarity is moles over liters. We have our liters, 1.25, but we don't have moles, but we do have grams, 50.0 grams. And we using our dimensional analysis, 1 mole weighs 58.44 grams. That's again our molar mass. And we take 50, divide it by 58.44, and we get 0.856 moles. We're going to take that 0.856 moles here, divide it by 1.25, and with 3 sig figs we're going to get 0.685, and our capital M for molarity, NaCl. So just to recap, they wanted the molarity. Molarity is moles over liters. We didn't have moles, we had grams. So we had to convert our grams to moles. We've been doing that now since our mole unit. In our stoichiometry, we know how to get grams to moles. We divide by molar mass. This is the molar mass of NaCl. It's got 1 Na and 1 Cl. We added them together and got 58.44 grams per mole. We put that moles, and then we divided that by liters, because that's what it is, moles divided by liters. And we got 0.685. Next question, they want grams. Well, to get to grams, we're going to kind of do this opposite. If you look, we're going to take our volume. Our volume is in milliliters. We don't want milliliters. We want it in liters. Why? Because molarity is in liters. So we're going to take our 250 milliliters, and we're going to turn it into liters, which is going to be 0.250 liters. And then I know that my molarity stands for moles per liter. So I'm going to go in 1 liter, that's what it means, I have 0.300 moles. That's what it stands for. Again, going right back up to here. That's what it stands for, how many moles there are in 1 liter. So my liters cancel. I don't want moles though, I want grams. And I know 1 mole of NaCl weighs 58.44 grams. That's my molar mass. So my moles cancel. So I'm going to take my 0.250. So this is not part of my calculation here at the beginning. I'll get blue and go ahead and cross it out. All I did was use that to convert. So I start with 0.250 times 0.300 times 58.44, because they're all at the top, and 3 sig figs. My final answer is 4.38 grams of NaCl is my final answer. My final problem here asks how many milliliters of 0.850 molar NaCl could you make if you had 30.0 grams of NaCl. If you've noticed, I've never started my problem off with my molarity, and that's probably a very good thing to notice. So I'm going to start off with my grams. What do I know? I have 30.0 grams of NaCl. what I want to do is convert those grams to moles. Why? Because I always want to get to moles. Now, using dimensional analysis, I know moles have to go on the bottom. What do I know about moles? My molarity is 0.850 moles are in 1 liter. Notice here I flipped my molarity. My 0.850 moles are on the bottom, but they're equivalent to 1 liter, excuse me. But they don't want liters, they want milliliters. So I'm going to go ahead, and I know 1 liter is 1,000 milliliters. So I take 30 divided by 58.44 divided by 0.85 times 1,000. Again, anything on the top I multiply, anything on the bottom I divide. Checking my units, and my answer with 3 sig figs is 604 milliliters of NaCl. So those are some sample problems. Again, if you struggle, you can use that triangle at the top. I didn't use it much because I like to rely on dimensional analysis. Some of you like dimensional analysis using the units. Some of you might like to look at that triangle to figure out what you're going to do, whether you're going to multiply or divide, whatever you need to get to what it is asking for.